Thank you, Manuela. Before starting, I would like to thank Ivana and Rotak for inviting me to give this talk, and more in general for organizing this meeting that is becoming a great success, not only for the subject, but also for the format, which is very much appreciated for the discussions and for what will be ahead out of it. Thank you very much. When I was invited to talk about complex terrain, first of all, and the achievements of the last 100 years, I was thinking on which are the sources where we find those achievements. And so I started thinking of the major textbooks or collection of articles that were very useful for many of us. And I would say that the first one that came to my mind was a review, a comprehensive article by Arthur Wagner, who was a professor at the University of Innsbruck in 1938, which put together a lot of existing theories and observations or daily periodic mountain winds, and provided a unifying theory of those, including some seminal concepts concerning the circulation across valley winds. And although at that time it did not include much of turbulence, nevertheless, it included many concepts that were quite seminal in the future developments. Later on, I would like to mention the well-known monograph published under the editorship of Bill Blumen in 1990 as an American Meteorological Society monograph as an outcome of the well-known ASCOT project, which was held in 1980s. And more recently, another collection of results reviewing the existing knowledge was published in 2013, edited by Stefan de Wecker, Tina Katopodoshow, and others. And more recently, following the TMAX initiative, a special issue of Atmosphere hosted a bunch of papers written by experts concerning the state of our knowledge concerning atmospheric processes and turbulence over complex terrain. And the most recent, I would say, comprehensive exposition of the state of knowledge is the paper appeared by Finnegan and other authors in Boundary Meteorology most recently. When we talk about complex terrain, we mean a variety of landforms and situations which cannot be encompassed by just one investigation. Indeed, if you look at the last, say, 20 years, you will see a series of major experiments that have been arranged to take measurements of different processes occurring in different situations, not only geographically, but also topographically. And you may see that most of them concentrate on different situations, maybe valleys, maybe slopes, maybe basins, and other situations. And this already is a signal of the complexity of the phenomena which are encompassed. When we talk about complex terrain effects, we should, first of all, distinguish between dynamically driven processes, which do not include as a major part any heat exchange. And among them, concerning turbulence, we should include also the wave breaking that has been already treated yesterday, or the effects associated with separation and rotor that were investigated under the REVEX, including wakes such as von Karman wakes that occur across mountain over the islands. Also, we can think of smaller scale processes associated with the flow over isolated hills. And this may have non-trivial situations associated with the separation of the flow and the turbulence. And these have been quite extensively studied in the last years. The atmospheric boundary layer of a complex terrain displays as a consequence a series of peculiar effects that are not easily collected under the same concept. To this purpose, it's very illuminating the paper by Manuela Lehner and Matthias Rotha, where they have introduced some criteria to identify specific processes of the so-called mountain boundary layer in an acronym MOBL. MBL was already taken by marine boundary layer, so we have another one. And I won't go into the details, but I invite you to read the paper, because there you can find how these dynamically and thermally driven situations may be significantly make a significantly different effect compared to the, for example, neighboring flat terrain. Again, when we talk about processes, we may also think of thermally driven processes. And these thermally driven processes are mostly dominated by the exchange of heat between the surface and the atmosphere, maybe either heating or cooling, depending on the situation. And again, depending on the kind of landforms that you consider, you may have different kind of motions, winds, such as slope winds in the simplest cases, valley winds, if you deal with a valley, whatever the form may be, basins, if you have closed basins, or plateaus, it's a complementary view of them, or even entire mountain ranges. For the purpose of the present talk, so concentrate just on the simplest one, slope winds, not only because they are most easily treated in short talk, but because they contain some standard concepts that are common to all the others. You may imagine that whenever a motion is originated from the exchange of heat between the surface and the atmosphere, what happens to the surface is the most important part of the electric flow. So, if we understand what is slope winds, we are on a full way to understand what happens in atmospheric physics. To focus on slope wind, let me start with this simplified picture by day-one analysis through quantum technology. And also, we imagine that during daytime, the heating of the slope will produce a temperature anomaly at the surface that, by transferring heat and buoyancy to the underlying atmosphere, produces wind, which will have a sort of jet-like shape in and then during nighttime, the opposite process typically occurs. You have the cooling of the surface, so you have a colder air layer developing near the surface, and you get to buoyancy effects. It produces both a temperature capacity and a drainage speed. In between, you need to imagine a transition situation, which is not a simple picture. Here, and we will see an example later. Notice that by saying so, we concentrate on the periodics winds. There are other kinds of winds, such as those that occur on glaciers or large ice expanse in the polar regions that do not follow, of course, a daytime period. Apart from the picture from Big One, we do get some concept that what we effectively allows to estimate the intensity of this flow. In this, in fact, we learned yesterday from Professor Battimelli that Ludwig was in the meeting in 1922, but there he spoke about airports and aerodynamic airports. But some 20 years later, he published his celebrated book, Theory portion. There he introduced, among many other topics, a concept of the flow occurring over a flat plate tilted by an angle alpha about the horizon. So he clearly distinguished between a situation which was quite familiar to him as aerodynamic fluid mechanicians that of no stratification. But then he included the case of a stratified flow, which, as we will see, is a crucial condition for the occurrence of a steady state over a flat plate that is heated or cooled. So the scheme is quite simple. You imagine for simplicity an infinite plate tilted by an angle alpha. You assume a steady state situations which may be depicted in the terms of the constant temperature anomaly the surface C. And then you expect to have whatever the G is fixed, a steady flow that will have some shape. So the uncontrolled conditions that you assume are those of a semi-stratified atmosphere, and you have gamma, which is one of the crucial parameters of the flow, and in the atmosphere at rest, if there is no flow. And let's keep in mind this because it will be very important in the point. Based on that, you can easily build up a room with some frequency that will be, as I said, another feature there. Then, for convenience, we adopt an S coordinate along the slope, positive upwards, and an N coordinate from the slope. Nevertheless, we also retain the vertical Z for whatever speed the traffic. So, if we assume all the simplifications that we have introduced, the first produced, and assume invariance, the budget of momentum and energy becomes very simple. And here you see the anomalies with respect to the steady state. So the budget of momentum has no acceleration, since we have a steady flow, And we only have buoyancy acting as an active force, and then we have the resistance offered by the viscosity. Energy balance implies the advection of colder air upwards and warmer air downwards along the slope, and which is balanced by the normal to the slope heat flux associated with the conduction. As specified above, this is speak in a laminar process. So what we have here are the molecular and the kinematic viscosity and the kinematic diffusivity of the fluid. But nevertheless, this model is very useful for us to combine all the mechanisms that are implied. So the combination of the two balances, advection and cross to the surface flux. The boundary condition to get the solution will impose the no-fluid condition of the surface and extract an anomaly, whereas as expected at infinity, we do not assume that any flow will appear and any anomaly of temperature will of course vanish. I explicitly underline the fact that a balance can be achieved only if alpha is equal to zero. So the problem cannot be applied for that place, because in that case you are not helped by the stability. Stability doesn't actually keep in the flow close to the plane. And also, you cannot have any flow of this kind if you don't have stability. For example, the current, which included the new situation, was quite exposed to convections. Not to well, if you make some calculations, you can come out with the simplified picture of the vertical profiles that are quite well known, that have some familiarity mathematically with the angle layer. The length scale is, of course, controlled by the parameters entering the equation. So the two diffusivities, the Bruch-Sala frequency and the inclination of the plane. As consistently, if any of these have to be not multiplication of no angle, the length becomes infinity, so it gets completely similar. The other terms are quite clearly similar. If L becomes very large, it means that the changes we have are quite high. And this happens typically with very small alpha numbers when it is, or with very strong influxes. Notice that, as expected, the anomaly in this linear model is controlling the amplitude of motions, maximum anomaly is at the surface in the case, and the strength of the velocity is proportional to c. Notice that this makes the flux requiring heat flux, either positive or negative. Consider that this model works both for heating and for cooling, consistent with the design. If you don't have any heat flux, you don't have a temperature anomaly, and so you don't have any flow. This is another important. You don't have a neutral flow in this condition. You can only have heating or cooling, so promoting the flow. It is interesting to note that the model the grant is a steady state, but you can extend it to non-steady state, including the time derivative is consistent, and in that case, there should be an illusion here. But, I'm sorry. Yeah.
Just trustworthy to click on it.
I'm clicking.
What's this? Maybe it's because of the laser here.
Oh,
Turn off the laser thing. No, the function on the computer. You turn it. Yeah.
When we try to
I mixed up.
doesn't work. Oh, thank you very much. So, when we look at the non-stationary situation, you find two very different conditions. One is the supercritical, when you have a very steep or very stable situation, and so you have a motion. Okay, you have a motion which is totally in phase, so the response is very quick. Whereas if you have a quite weak coupling between the surface and the atmosphere, you may have significant delays between the evolution of the bottom and the evolution of the upper layers. And this has been also seen, especially in the transition in the application. At the time of Rao, there were no measurements to compare with about the goodness of the model. But they were taken soon later by experimenters in Innsbruck, and in particular, we worked out at different. And they compared measurements taken over the North with the observation with the theory. And we had quite a good agreement during nighttime when we have stable situation, whereas the daytime is somewhat compatible from was not as good. That approach was pursued further more recently, and Franco Crisopoulos and Dino Zardi working on catapactic interpretations adopted a more sophisticated approach, WTB solution, and they actually found out that you can still adopt a solution like the proposed plan, provided you use a K, which is not constant, but depends in the O'Brien form in height, and you include that in a suitable integration that allows you to get some profiles closer to realistic ones. Here you can see the comparison with data taken of tensor anomaly and velocity taken from two kinds of predictions, one in Austria and one in Iceland. And this is quite good. Notice that in any case, K is a constant feature defining totally the flow. A similar approach was also more recently adopted by mutation on the error cohorts in working on data from an elevated slope. They proposed a change in the length scales, and so they adopted a similar feature to it, but the length scale was actually controlled again by the two eddy diffusivities and the viscosities, including a linear correction, so a non-constant one, which acts both here and here. So you can acknowledge the length scale modified by this way. They tested those on measurements taken along the slope, and they found, I need to run because time is absent, a very good agreement, both for what concerns velocity and for what concerns the temperature anomaly. Also, they were able to take measurements very close to the surface by means of a device, which is actually a Python tube very carefully calibrated, and which will be very useful to understand the exchange processes near to the surface. In particular, they could compare data with a standard logarithmic profile in the case of half surface or resolution surface. However, this application seems to say that all of these fluxes are not amenable to the classical solutions of a flat length offered by Monin-Obukhov similarity theory. In particular, yesterday, Ivana gave us many evidences of the fact that, for example, the fluxes are not invariant with height as required by theory, and as a consequence, also the vertical profiles of velocity and temperature are not easily amenable to the standard similarity solutions. But to understand why this seems to be the case, it's good probably to get back to the Monin-Obukhov similarity theory, which was quite recently reviewed in a well-known paper by Prof. If we want to summarize the theory, we can use these three equations actually. And the fact that should be clearly acknowledged is that in any case, the Monin-Obukhov similarity theory is a sort of adjustment of the neutral solution in the case of non-neutral conditions. So you start from the logarithmic actual profile and you correct the logarithmic profile depending on the heat fluxes, which assumes that in the absence of heat fluxes, you have nevertheless a wind, which is not the case of the slope winds, as we have seen. Also, the length scale, which is usually written like this, contains two elements which are not essential. Minus signs of the K that have been introduced customarily, as pointed out by Cadre Young in 1990, but are not really essential. They are retained just for customary reasons. So the two similarity functions can be used also to build up suitable eddy diffusion coefficient, the eddy viscosity and eddy diffusivity. So you may think of similarity functions as corrections of the diffusion coefficients instead of correction to the non-dimensional gradients. So how can we apply the basic concept of Monin-Obukhov similarity theory to a slope wave? Let's do exactly as we could find in any textbook to be Monin-Obukhov. In the case of flat homogeneous horizontal surface, we get the invariance of stress and of heat fluxes with height, from which we define these two constants that are the stress and the heat flux, or for simplicity, the friction velocity and the friction temperature. Notice that the two constants, tau 0 and hs, are totally independent boundary conditions. You may have whatever value of both. There is no physical constraint. So you have one U star and whatever heat flux, or vice versa. There is no connection between the two. These two are integration constants, so they refer to the state at the surface, and they are independent. So typically, in the very basic condition, that of the very flat place, you don't have to specify Z0, which is another constant. You have a viscous sublayer and an alpha sublayer and then a fully turbulent layer. And so you assume that in the viscous sublayer, you have a solution like this, which is just the first part of a series, time series, also the Taylor series expansion. And for the upper level, you have the T. Now, let's think of applying the very same concept to a tilted flat plate. Things are quite different. First of all, because these two terms appear that did not appear in the array. So if you set to 0 these two, you find again the invariance with height. But if you have an alpha different from 0, these terms do come in. So the invariance with the normal order still holds, but the of the total quantity here. So let us assume for simplicity that we neglect the buffer layer. So we assume to have just a viscous sublayer, and then on top of it, at the level NV, we have the connection with the upper surface layer. So we do not expect to cover all the jet-like shape of the slope wave. We just want to see what happens in the very lower layer. So if we concentrate on the viscous sublayer, of course, the dynamics is the same as depicted by Planck. It's the lambda one. But the boundary conditions are different, because at the bottom you have the same boundary conditions, but on top you have the matching with the turbulent surface area, not vanishing at infinity. So the two critical quantities will be the delta Ts and the one U star that you can easily define. Now let us work as we did in the viscous sublayer at flat terrain, working with the derivative